Philippines. Hello, this time I'll be able to have, another topic in which this is only another overview because I discussed a little bit about of thermodynamics. Okay, so we need to know about the concept of thermodynamics. So first and foremost, we need to understand the term thermodynamics. So we need to separate the word thermo from dynamics. So when you speak about thermo, meaning that is heat, okay, meaning heat energy, and then dynamics, meaning motion. Okay, there's a motion of molecules. Okay, motion of a molecular energy, something like that. So heat and motion. Okay, something like that. So in a phases of matter, so solid, liquid, and gas are having its motion. Okay, so thermodynamics are applicable in solid, liquid, and gas. Okay, like that. So this is also very, very essential in studying heat transfer. Okay, if we have basic concept in thermodynamics, then we can easily understand the heat transfer such as the conduction, the convection, and the radiation, something like that. Okay, so we know already and we are very, very familiar with the formula of heat, right? In our chemistry. So we can also apply that here, but there's a slight difference. Okay, depending on the derivation. Okay, the heat is equals to the mass times the specific heat capacity times the delta change in temperature. Okay, that's the formula of heat, right? Very basic. Okay, now, so in the morning, a while ago I discussed about the laws. Okay, but actually there are four laws of thermodynamics, not only three. Okay, four. But the zero law of thermodynamics is just very basic in our day-to-day life, something like that. Okay, so of course, before having an adequate concept for this thermodynamics, so let's define first what is really thermodynamics. Okay, thermodynamics is a science, okay, that describes how thermal energy is converted or transformed from one form to another in a matter. Okay, meaning in a phase of matter, it's solid, liquid, and gas. Okay, meaning thermal energy really. So if you speak about thermal, there's heat energy. Okay, and governed by the changes in temperature, right? Because that's a thermal. Okay, so our driving force is the temperature gradients from high temperature to lower temperature. Okay, let's explain first the zero law of thermodynamics. Okay. So let's understand first the basic before going to the problem solving. Later we'll go to the problem solving. Oh my gosh. Hello guys. Going back to the first law of thermodynamics. In the first law of thermodynamics, talking about thermal equilibrium. Okay, temperature changes is very important, something like that. Okay, so there's a thermal equilibrium. So if we take into consideration, there are three systems to be considered. For example, there's this A, wait, A, B, and C, like this. This is A, B, and C. So this is zero law of thermodynamics. So this zero law of thermodynamics A, B, and C. So we have thermal equilibrium. Okay, the A system with respect to the temperature is equal to the B system with respect to the temperature at B is equal. So TA is equals to TB, meaning thermal equilibrium with respect to temperature. Okay, so T so this is thermal equilibrium at system A is equals to thermal equilibrium at system B with respect to temperature as our driving force. So we can also say that thermal equilibrium in system B is equal to thermal equilibrium in system C. Okay, we can also say that the thermal equilibrium in system B is equal to the thermal equilibrium in system C. So therefore, we can say that thermal equilibrium in system A is equals to thermal equilibrium in system C, like this. Okay, so therefore thermal equilibrium in system A is equals to thermal equilibrium in system C. This is with respect to the temperature changes. Okay, then this will be in cycle of the equilibrium will be in cycle, something like that. Okay, so this is the zero law of thermodynamics. Okay, the example to this is, for example, if I will put one glass of hot water now and another also one cold water in a glass with the same volume, the same amount, and then I have air condition. So time will come, their temperature will be equal. Okay, with the same temperature with the air conditioning equipment or the AC. Meaning to say the temperature of the AC will transfer to the temperature of these two glasses, okay, of water. So equilibrium with each other, thermal equilibrium with system A, which is the hot water in a glass. Okay, thermal equilibrium also where the system B, which is the cold water in a glass. Thermal equilibrium also with the temperature of the AC. So this is cycle like this. Okay, in this cycle, C is the air conditioning as our specific example. A is the hot water in a glass. B is a cold water in a glass. Okay, so this will reach thermal equilibrium with each other. Okay, something like that. So that means that the transfer really is from hot to cold because the hotness of hot water will become normalized, and then after that it will really become cold to receive the temperature of the AC, something like that, of the air conditioning temperature. Okay, within the environment. this room of mine is the environment, temperature environment, okay? So it will really transfer to this two glasses of water, the hot and the cold. So this is a very basic example. Another example also for this zero law, right? More on Fury. Okay, so this another, if you have a container, let's say this is a container. Okay, now it's a container. This one is a container, right? Container or a vessel, something like that. It's a container. Okay, there's a container and there's conductive substances inside the container with respect also to temperature. Let's say for example this is one. Okay, conductive material 1, this one. Conductive material 1 with respect to temperature. Okay, and conductive material 2 with respect to temperature, like this, and conductive material number 3 with respect to temperature, this one. Okay, so since we are now in thermal equilibrium, so conductive material 1 with respect to temperature is equal to the conductive material 2 with respect to temperature. Okay, this one. C stands for conductive. Okay. Conductive material 1 with respect to temperature T is equal to conductive material 2 with respect to temperature. And now, conductive material 2 with respect to temperature is equal to the conductive material 3 with respect to temperature. This one also. Okay? Conductive material 2 with respect to temperature is equal to the conductive material 3 with respect to the temperature. And suddenly or consequently, okay, we can say that conductive material 1 with respect to temperature is equal to the conductive material 3 with respect to temperature, this one. Like this. Conductive material 1 with respect to temperature is equal to the conductive material 3 with respect to the temperature. Because these are all conductive materials are inside a container. So they will share their respective temperature and they are also in equilibrium or thermal equilibrium with each other. So these examples of zero law of thermodynamics. So the illustration on the left side and the right side are just having the same explanation, theory and concept. Okay, that's zero law of thermodynamics. Okay, so there's a transfer of the molecular temperature. Okay, from higher temperature to lower temperature. It's gonna be like that for the temperature gradient. Okay, something like that. And now we go to the first law of thermodynamics. This is the most widely known topic of thermodynamics. Okay, apart from the, let's say, the second law of thermodynamics. Okay, the second law of thermodynamics, okay, are talking about the introduction about heat energy. Okay, heat energy. So the heat energy Q is equal to the delta change in the internal energy plus the work in the system. Okay, so that is first law of thermodynamics. So this is a mathematical example for the first law of thermodynamics, but the statement, theory and concept is based on law of conservation of energy with the analogy of the law of conservation of matter also. Instead of matter, we will use energy. Okay, Okay, law of conservation of energy, or this is the first law of thermodynamics. Sorry, the first law. Okay. In the zero law of thermodynamics, it says that if you put different various substances in the same container or in the same vessel or the same environment, okay, with respect to different temperature, time will come, they will have a thermal equilibrium with each other. That's the statement, okay? But in the first law of thermodynamics is the law of conservation of energy derived from there, okay? First law of thermodynamics, okay? That's where the formula is are all energies. Heat energy, internal energy, and the work. These are all energies, right? As we can remember on physics discussion, right? Okay, energy is the capacity to do work. Therefore, work is equals to energy. And it's also included in the formula here, right? Because I said earlier, okay, heat energy is equals to the change in internal energy plus the work of the system. Okay, so first law of thermodynamics. I don't have to put the statement, guys, but you should also memorize this statement because this is very uh, basic. Okay, so as we can remember, except for the law of conservation of momentum, law of conservation of kinetic energy, this law of conservation of energy, example is law of conservation of kinetic energy, and law of conservation of mass in chemistry, right? And law of conservation of matter in chemistry also. Okay, in physics, law of conservation of kinetic energy, law of conservation of energy, law of conservation of momentum. Okay, something like that. So there's a lot of law of conservation, chuba chuchu, and you need to inject that in your brain cells because it will come out in the examination also, especially in engineering courses that have Philippine Regulation Commission board examination. Okay, so the basics will be there always. In fact, there are more theories than problem solving. Okay, in the examination. And some are very easy to solve, only like this, and then you can exactly choose the correct and the best answer. Okay, first law of thermodynamics, it states that okay, energy can neither be created nor can be destroyed, but it can only be transformed into various forms of energies. That's what I told you. Okay, from potential energy to kinetic energy to heat energy to sound energy to internal energy to thermal energy to radiation energy to pneumatic energy, hydraulic energy, to acoustic energy, geothermal energy, hydrothermal energy, light energy, chemical energy, mechanical energy, and electrical energy. There's a lot of energies, right? This is under our first law of thermodynamics, or under the brand banner of the law of conservation of energy. Okay, so instead of the word by means of physical or chemical means, we just substitute that with our words, but it can only be transformed to various energies because it's just the same with the law of conservation of matter. That is our parent, okay, theory that states matter can neither be created nor can be destroyed by ordinary chemical and physical means. But in here, we remove the by ordinary and chemical and physical means, but it can be transformed to various forms of energy in this law of conservation of energy, which is specifically the first law of thermodynamics. Okay? But in thermodynamics class, this is really a science that describes the thermal energy, how it is being converted to form one another kinds of energy, to form one another kinds of energies like this. Okay? It could be converted and transformed to another form of energy, something like that. Okay? In a matter, solid, liquid, and gas. Okay? Matter nga na ang determine solid, liquid, and gas. So it could be a state of matter or phase of matter. Okay? Oh my gosh. So phase and state is just the same, ha? For example, there's a question like this. What are the three phases of matter? Your answer will be solid, liquid, and gas. Okay? Or what are the three states of matter? Solid, liquid, and gas. It's just the same. Sometimes other books also, what are the three stages of matter? Should be solid, liquid, and gas. Only changing the terms, okay? But the same concept, okay? Something like that. Okay. And then the formula for this, and that was a statement theory about first law of thermodynamics. And we have the scientific law, meaning the formulas is this. So Q is heat. Okay, whether in physics or in thermodynamics or in chemistry. Actually, chemistry is also studying also heat. Okay, and this is very popular until physics, thermodynamics, until unit processes and unit operations also involves heat there, especially in heat transfer. Okay, like that. So Q is equals to delta change in internal energy. Okay, plus work. Okay, like that. That's why physics is prerequisite to the major subjects. Okay, because this will be useful, physics and chemistry all the time. Okay, if you will never pass these subjects, then you can never take those major subjects. Okay, related to sciences. Okay, like this. So this is the scientific law. Scientific law is the formula and equation. Huh? Okay, you can never have the scientific law, equation, and formula if you don't have the scientific theory, principle, and concept first. Okay, that would be the last, because this is already the interpretation of your scientific research and discovery. The scientific law is the last step, meaning you conclude, you summarize your scientific research and discovery. So you have scientific law in the end. Okay, so theory and concept will be the first, and then this is the last. Okay, so that's called scientific method under scientific research, right? Okay, so this one is very useful, huh? This first law of thermodynamics. Okay, like this. And our second law of thermodynamics, it talks about the entropy. Okay, entropy is being studied also in physical chemistry, because this is really the physical attribute of the molecules, or physical features of the molecules, whether it is a solid, liquid, and gas. Okay, so for example, liquid, there's a lot of molecules in the liquid compacted with each other, bombarded with each other, collided with each other. So in that manner, there's a high intermolecular forces, then higher kinetic energy. Okay, so it's higher kinetic energy, then the collision is faster, then there's a very, very high randomness and disorderness of the motion and the movement of those molecules, and this is entropy. Okay, it's very clear. The randomness and disorderness of the molecules during the bombarding of the molecules and collision of the molecules in liquid or in gases, that's called entropy. Okay, so this is the main concern of the second law of thermodynamics. Again, theory. Okay, because in this theory we can really apply what particular formula you will be able to use in the problem solving. You can easily interpret. Okay, if you have the laws of thermodynamics in your mind, it's very easy to apply. Okay, and then you will be able to have your analysis, then bingo, you can solve what is being required on the problem. Okay. Actually, ito tuyok na mo ana, pero it goes back to the concepts, theories, and principles. Okay? You are only directed to memorize the formulas, okay, but you have to understand the concept and theories. Okay? like that. Because if you'll never memorize also, it will take time for you to get the correct answer. Because mag-derive pa ka. Okay, you should derive to come up with this formula. What if you memorize so that you can easily get the formula? Anyway, you understand the theories and concepts and principles. So even though it will be mixed and rumbled, and you can understand, right? So it's better to memorize the formula. Okay? And then after memorization, have the relationships analysis. Relationships meaning, could it be inversely proportional with each other, directly proportional with each other? So try to manage the understanding of the relationships also. For example, if I will increase the pressure, what will happen to the volume? Something like that. Because in the problem solving, you will get the answer right. And then if your answer is not valid, because the pressure is expected to be high and then your pressure is lower, so it's wrong. Okay? Meaning, even though you're using the formula that you are expecting that is correct formula, but that is not really the correct formula. It's not applicable to that kind of problem. Okay, it's gonna be like that. Even though you get your answer also closer to the choices, like that. So be careful also. Okay, something like that. Okay, so I love heat transfer and thermodynamics really. Okay. Okay, going back to the first law of thermodynamics, this one. So in first law of thermodynamics, this we discussed, huh? Okay, this one. Okay. This one, law of conservation of energy, and the first law of thermodynamics. In the second law of thermodynamics, guys, what is all about? That is an introduction of entropy, as I told you, right? Entropy. Okay? Okay, don't you call entropy? Wow. Okay. Another example also of entropy is, for example, if we have so many things in our minds and we're very, very stressed or thinking too much things in our mind and then accumulated in our brain cells, because I have so many work like that, and I have problems like that. So that's also one example of entropy, randomness and disorderness of thoughts in your brain, something like that. So that's also entropy, meaning it's not in proper order. It's random or disorder. Okay, like if we try to put this in the momentum transfer or the fluid mechanics or fluid dynamics, this is gonna be a turbulent flow. Okay, this is a really not in a steady state flow, not in a organized or steady state flow like this, and then very fast moving, something like that. Chaotic, chaotic, chaos, something like that. Okay, random. Okay, so second law of thermodynamics, and I have to show you the formula for this, and I have to state also the statements, theories, concepts, and principles. Also, second law of thermodynamics. Okay. What really what really confusing, guys, is when the examination are being compiled and compressed already. Okay, because you will confuse what problems to be used, like that, because there's also quantities that's related to this, like that, and then sometimes you will be tempted to use the other equations that is also closely related to this, and then the answer will not be the same as this. Okay, because also in chemistry and physics there are also theories that are reverse. Okay, for example, the work done by the system, ganun siya. Okay, the work done by the system in physics is gonna be positive, and then in chemistry it becomes negative, and then work done on the system is negative in physics, but in chemistry is positive, like that. But then if they try to put that in the problem solving in the examination, of course you will confuse with what concept you will be able to use. So the only way to do that is to consider the other assumption, okay, and other conditions there, okay, because it's stated there also, and and the given also it's there. You can feel also that this is gonna be like this kind of problem, then you can attach this theory and concepts for that, okay, because they're also contradictory, especially the sign, okay, positive and negative, okay, but little only few, okay, but in this case, especially thermodynamics, there's a reverse also in the chemistry, ha, okay, especially the work, okay. And then for the heat, not necessarily because the heat, for example, heat added to the system, okay, it's positive man siya. The same as sa chemistry, right? So heat added meaning the heat is being absorbed because it is added, right? It is absorbed. And then heat is removed, meaning to say it is being dissipated or it is being given off or released. Yeah, like that. So it's just the same. But they're using the other terms, which are the exothermic and endothermic there in chemistry. Because talking more in chemical reactions. But here, it's just heat removed, heat added, okay, something like that. But in terms of energies, the units are specifically joules, Joules, or the calories. But most of the times joules. But in chemistry, a lot of units to be used there. Okay? So, right? The BTU, like it like that. So, with British Thermal Unit. Okay? And then sometimes using ERG as energy. Okay, like that. So, but here, always joules, kilocalories, like I said, because it's energy. Okay? It's very important energy. We can never do our work without energy, right? So this topic is very interesting. Okay, so second law of thermodynamics. Because without heat, guys, without heat regulation in our body, we will die. Inside our body, we have a body core temperature to at least, I think, 37 degrees Celsius, something like that. And then it should be in equilibrium to the temperature in the surrounding. There must be a balance, okay? And if we don't have that enough temperature to regulate well, then we will die also. For example, your temperature is very high, then you have already a fever, okay, you are sick because your body temperature is not yet regulated well, okay, like that. So this is to have a good cycle of your heat energy inside your body, okay, heat energy, okay, so you will release that heat, okay, and then we're going to equalize that or neutralize that with a cold environment, okay, for cooling system of your body. We need cooling system, okay, not only the equipment, the machine, we as individual need cooling system in order for us to have a better regulation of our temperature, body core temperature, something like that, so that we can have an adequate heat energy during our metabolic cycle or metabolism, okay, so that we will become healthy all the time. So this is related also to thermodynamics, okay, in terms of physiological points of view and in the anatomy study of human being, okay. It's also biochemistry because biochemistry is studying also thermodynamics in that part only, specifically focusing in the body of an individual. But here more on the focus on more on the process, okay, process on the plant, on the company, on the factories, blah blah blah, systems like that, fluid, liquid, solid, and gas, not inside the body, okay, but through physical and chemical processes, or what we know as chemical process industries, okay. In chemical process industries, whatever products that the company or factory is producing under this, thermodynamics are always be there because it's heat, HEAT, okay. Without heat energy, we cannot produce products, okay, 100% sure, okay, because through heat energy, okay, the chemical energy will be converted to mechanical energy. The mechanical energy will be converted to electrical energy and light energy. So we have the light here. It started with chemical energy. The components of that made it move, so mechanical, and then transformed to electrical energy, and then light energy is lost. Okay? Electrical energy is more on the electrons flow, current, but the last will be the light that we can see in our eyes. Okay? Chemical energy, mechanical energy, electrical energy, and the last will be light energy. Okay, in case of this fluorescent, okay, light or incandescent bulb. Okay, the same with the purpose of the motor pump of different equipment. For example, generators, diesel generators, whatever, power generators. Just like this, just started really with chemical energy because of the fuel, F-U-E-L, or the battery itself. Okay, battery system and the fuel systems are under chemicals. Chemical reaction first. Okay, without chemical reactions, we don't have power. Okay, or electrical power. So the starting point really is chemical. Okay, so the parent of all energies are chemical. Okay, so just like the photosynthesis reaction also from the plants, it started with chemicals for the adenosine triphosphate, ATP. It produces carbohydrates in order for us to eat those foods coming from the plants. Still chemicals, okay? So to give us energy, okay? Like that. Mechanical energy is not on the first, it's the second, like this. Electrical energy will be in the third, and then the light energy will be in the fourth, blah, 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 so and so. But all started with chemical energy, okay? Interesting, right? Okay, the second law of thermodynamics. Okay, like this. So, time check brought to you by Pablo Lascanda. Okay, so in the second law of thermodynamics, there is an introduction known of an entropy. Okay, delta S. Okay, delta S is equal to the change of the heat energy over the time, or Q over T. Okay, again, entropy delta S is equal to delta change in heat over time. So meaning to say, this is also a rate. Okay, you remember that I explained to you over and over again. So if I will say the rate of change of heat, so your answer also will be, okay, your answer also will be entropy. Okay, so because a lot of questions will always come out in the examination. The rate of change blank, the rate of change blank, the rate of change blank, the rate. Also here, the rate of change of this is thermodynamics. Okay. Okay. Entropy, introduction to delta S. Oh my gosh. Entropy. So say again, what is the entropy of the system if the temperature of this substance like this from 20 degrees Celsius and the heat is and the energy consumed is 230 joules. Oh, you can compute already the entropy as easy as that. Okay? Ganun siya. Chuba-chuba. Okay? So, ganun lang siya. Ilan-ilan lang siya. Saan man sa kidali, man sa gigta kita mailad ko din nagkakuan, i-rumble na bitaw, so we will get confused also. If not, all of the examiners will be perfect and all will become top-notchers. But why only few will become top-notchers? Because a lot also will be confused. And majority will be confused, of course. For example, there are 800 who took the examination and only top 10 are only the top. Imagine, where are the other 700? Meaning 700 plus are got confused. Only 10 are doing well in understanding the, the perfect theory and problem solving. Okay, so this is the they try to trick the examiners, and their job also is to regulate, really regulate, meaning to regulate the passers, so that that's required in the industry. and also a business also, because after that they will take again and pay money for those agency that who regulated the examination, something like that. Okay, business and regulation. Charot. Okay, sa entropy, nahurot na dyan akong pentilpin. Entropy is equals to Q over T. Ganun siya ha. Okay. This is the entropy class. Okay? Okay. It states that the sum, statement na tayo because we have illustrated already the mathematical or the scientific law. Okay? It states that the sum of the entropies in the systems of the surrounding will always increase. Okay, like that. Or in a general point of view, the entropy in the system of the universe is always increasing. Wow, universe talaga, June? Yes, randomness talaga sa outer space. You cannot expect there a very, steady flow on the orbits or whatever, because there's a lot of steroids like that. Not steroids, what do you call asteroids? Because steroids is in the lipid, okay, in the macromolecule study of biochemistry. Okay, sorry. It sounds the same, steroids and asteroids. But asteroids, I mean, a lot of asteroids there, and then comets, like that, okay. Little bit deeper, small little deeper, kinds of stars, right? And then kinds of undiscovered planets also. There are also undiscovered planets, okay, aside from the 9 planets that we have, okay? So a lot there in the outer space. That's the most number one example of randomness and disorderness in the outer space. That's why it states in this second law of thermodynamics, okay, the entropy in the system of the universe is always increasing. Oh, so meaning to say, it's always in random motion. Okay, disorder, something like that. Okay, so if we put that into the face of matter, it goes like that. The sum of the entropies in the system of the surrounding is always increasing. For example, in my room, like that. So there's a randomness. Every time the paper will fall, and sometimes there's a dust coming in, like that. So we cannot expect sometimes it's become dirty, like that. So that's randomness and disorderness inside the room. Not only inside the toilet, the ground, the workplace. So if that is the case, if there's no randomness and disorderness, so housekeeping is not needed. Okay, or cleanliness is not needed. That means every day, every seconds, every minute, there are entropies in our environment, in the surrounding. There's randomness and disorderness, and it's really exist, something like that. Or else everything will be in proper order, right? Okay, so that's the principle of the second law of thermodynamics. Okay, entropy. Okay. So, second law of thermodynamics. Okay. Now we have to go to the third law of thermodynamics. Okay? But in the second law of thermodynamics, guys, there's another formula also aside from this. Okay, but I got a little bit confused. Charot. Where to put this one, but I'll try to have my own analysis. Okay, because I'm a bit confused between second law and the third law of thermodynamics, because it's not clearly discussed in the textbook also. Okay, because in the second law it touched also entropy, and in the third law also it touched also entropy. Okay, I will show you the third law of thermodynamics. Okay, third law of thermodynamics, it's up to you where you will apply, but I think it's second law of thermodynamics. Okay, let's justify na lang, no? Let's interpret. Okay, third law of thermodynamics. Okay, I think it's in second law of thermodynamics, really. Okay, but wait. Okay, so third law of thermodynamics states that according to Nernst, Simon postulates. Grabe. Nernst Simon theory. Okay, theory. Okay, don't forget this person, because he is the one who discovered, okay, that the entropy of the perfectly crystalline solid and substance under absolute pressure or absolute temperature, something like that, or absolute zero is equal to zero. The entropy is always equal to zero for that perfectly crystalline solid or substance at absolute zero, meaning temperature 0 degrees Celsius and atmosphere 1 atmosphere pressure. Okay, remember that one? At STP, standard temperature and pressure. For example, you remember your physical chemistry, right? I think one. Okay, an ideal gas law, like this, 1 mole of an ideal gas law will occupy 24.414 liters of a gas. So this standard will be always used in ideal gas law. And you can compute through that equation. PV is equals to nRT. That's based on at STP. Standard temperature and pressure. The temperature is 0 degrees Celsius. The pressure is 1 atmosphere. So the same here. Okay, the perfect crystalline solid substance, okay, at absolute zero. When meaning of absolute zero, that is temperature is equal to 0 degrees Celsius. Okay, is always equal to zero, the entropy. Okay, delta S is equal to zero. So that means, since third law are focusing on crystalline substance siya, so it's gonna be in the second law of thermodynamics yung enthalpy. Okay? You know enthalpy? Enthalpy had energy, right? Okay? The enthalpy of the system. Okay, now, it's in the second law of thermodynamics pala siya, in which we talk about Gibbs free energy or delta G. Ayay, dito na tayo sa delta G. Delta G. Okay? Delta G or Gibbs free energy. Wow! That's why we have 2 Gibbs, 3 Gibbs, like that when we do our personal loan. Okay? I think this derived from this energy. Gibbs, same spelling. This is Gibbs free energy. Charot lang ako rin. Okay. Gibbs free energy is equal to, ay nako, change in enthalpy. This is heat energy ha. And pag enthalpy ganito, automatic heat energy ganito na siya. Okay? So, minus the Q. Okay. Delta H is enthalpy and there's also heat. Malibog na ka. Kaya duha na ang heat. Okay, but remember this Q is the driving force is change in temperature siya. But this delta H enthalpy driving force is heat or energy. Could either be in the positive or negative heat energy. That's the difference. It's not direct on the temperature. But the heat on the other side is more driven on the temperature gradient, final temperature minus the initial temperature, the heat. Okay, but this delta H enthalpy driven on the heat energy. Okay, so that we can, there's a slight difference, but it's just more closer with each other. Okay, like that. So, Gibbs free energy in joules is equals to the change in enthalpy minus heat. So, since I give you the formula already for the entropy, okay, so we need to solve for the heat, right? So heat is equals to the change in entropy or delta S times T, substitute that there. So we have a new formula which is Gibbs free energy is equals to the enthalpy minus delta change in entropy times time. Okay? Okay, ganun siya. This will be the most common use na in the second law of thermodynamics. Gibbs free energy is equal to the delta H, or the change in enthalpy, minus the change in entropy times the temperature difference or temperature gradient. Final temperature minus initial temperature. So don't you worry because I already discussed to you how to compute temperatures already, That's why I told you memorize that in your brain cells. The degrees Celsius, the degrees Fahrenheit, the Rankine, and the Kelvin. Degrees Rankine and the Kelvin, 4. Okay, and the values also with the pressures so that it will be continuously used in all kinds of higher sciences subjects. This temperature and pressure always all the time. And the constants also. Okay? The density, ganun, chupa-chupa. Okay? So, third law of thermodynamics, entropy is equal to zero. Discovered by Nernst, N-E-R, and S-T, Nernst. Okay, Simon theorem or postulate. Okay? And the thermodynamic processes that the pure or the perfectly crystalline solid substances will have entropy equal to zero at an absolute zero. Okay, absolute zero meaning again at STP or temperature equal to 0 degrees Celsius. Okay, meaning at I think it's freezing point. I think so. The freezing point of water is 0 degrees Celsius, right? As far as I can remember. We should memorize that the boiling point, like that. The boiling point is 100 degrees Celsius. In water, at least the physical properties of water, guys, you will memorize everything, because water is very easy, and most of the time it will be used all the time. Memorize the, the specific heat value. For example, 1 calorie per gram degree Celsius. That's the specific heat of water. And the density at 4 degrees Celsius will be, already kept on repeating that one. 1000 kilogram per cubic meter density, 1 gram per cc, 1 gram per ml, something like that. Okay, and then also the, the density in terms of pound per cubic foot, 62.43 in English unit, right? Ganun siya. And memorize that also. Okay, so it's easy for you to substitute values in a basic equation, something like that. Okay, for water, it's very easy. Okay, and then you can also memorize a little bit with air. Air, because air is composed of 79% nitrogen and 29% oxygen. 21% oxygen, 79% nitrogen. Okay, now the air is not like that already because of pollution. Pollution. There's a lot of gases existing in the atmosphere, then it can also eat up some particles and molecules of this nitrogen and oxygen, so they will combine that there. That's why it's not already perfect 21% of oxygen. The evidence for that, when, for example, me as an OSH engineer, I conduct gas testing, the oxygen will never become perfect at all at 21% by volume. Okay, because there's a lot of gases existing in the atmosphere that try to displace the molecules and the particles of this oxygen gas, then problem. Because no problem with nitrogen. Nitrogen is an inert gas. It's not reactive. That's why we have nitrogen gas cylinders. Nitrogen gas is inert gases. Okay, noble gas will never react stable by themselves. Okay, the only problem is for suffocation and asphyxiation. Okay, annihilation and breathing. Okay, ganon. Okay, so that's the purpose. Okay, but in the purpose of computation and chemistry, it's always perfect all the time. 79% nitrogen by volume, 21% of oxygen by volume, ganon siya. Okay, then the basis of calculation will be 100%, something like that. It could be percent by mass, percent by volume, chupa-chucho, ganon. Because it has always have a basis of calculation. Okay, like that. So, going back to the entropy is zero for the pure or perfectly crystalline substance or solid by Nernst, Simon. Maybe it will come out. Who discovered that the entropy of a pure crystalline substance is always equal to zero? The entropy is equal to A, blah, blah, blah. Mawala ka na, kaya wala ka nag-memorize. Okay? You should memorize the contribution and the discovery of different scientists. Okay? So from now on, if you'll be able to take the board examination, memorize all the scientists and their contribution. Okay? Like that. Okay, for example, who is the father of biochemistry? Okay, Alexander Newberg, maganon siya. Who is the father of modern chemistry? Okay, Anton Lavoisier. Ganon. Who discovered penicillin? Alexander Fleming. Okay, who discovered X-rays? Ganon. And Roentgen. Who discovered radioactivity? Henry Becquerel. Who discovered proton? Ernest Rutherford. Who discovered hydrogen? Henry Cavendish. Who discovered oxygen? Okay, like that. Jules Priestley. Something like that. Okay, you should memorize all the sentences and their contribution. And then who discovered the vulcanization of rubber? Charles Goodyear. Or something like that. Okay? So, who discovered the ammonia process of reacting hydrogen gas and ammonia? It's Mr. Haber. Haber process na naman siya, reaction of ammonia and hydrogen gas to produce fertilizers in chemical process and industries. So you need to put that in your brain cells when you are still students so that you can remember that one when you're facing science examination. Okay? So load your minds with theories, concepts, and principles first, and then touch the problem solving later. Okay? It's gonna be the technique in passing examination. Okay? Now we have the kalas na siya. Third law. Third law naman kutob, may fourth law. Okay? May fourth law. Okay? So there are 4 laws of thermodynamics, the 0, the first, the second, and the third only. And now I'll be able to discuss another topic, which is the thermodynamic processes. It's in there that we need to pay attention. Okay, we need to pay attention because it's in here that requires graphical illustration. For example, if it is an adiabatic process, blah, 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 so and so, then you have to locate the graph, okay, something like that. You have to apply the different equations applicable to that certain system. Could it be adiabatic or isothermal, okay? And later we'll be able to solve problems also, okay? So by the way, class, this thermodynamics has been requested of one of my viewers in YT channel. So I don't have a plan to to live stream this one, okay? But due to his request, I do the vlogging and live streaming because I love this also because this is the basis also of heat transfer. Okay, and heat transfer is one of my favorite subjects in chemical engineering under transport phenomena. I like this so much. Okay? So, thank you so much. If you like this vlog and live streaming, then you can comment down below in the comment section. And if you're not subscribing yet, then you can subscribe my channel. And then you can click for some news updates of every singer, eternal voice, where everybody get the gladness, something. Gosh. Ganon.